don't know if you guys talk to yourself or not, but I do. When you're schizophrenic, you talk to yourself. And I'm the most interesting person I know, so I talk to myself a lot. And I'm trying to be humorous, but I'm not making it very well. Okay. So going back to this. All right. So yesterday, we talked about some of this material, and I want to go back to wherever it is. Just a second. Yeah. Okay. We were talking about this yesterday when last we spoke. And one more thing while I'm at it. We have everybody here, so in terms of not wasting any more time, let me take a snapshot of you guys. I need to get rid of the chat and take a picture. Capture window. Okay, you've got your attendance taken care of, so I can quit worrying about that. All right. Okay, so I'm going to give you some pictures in a minute about these concepts. So the concepts yesterday I tried to talk about was symmetric neighborhood, interior, exterior, boundary, accumulation points. And so that's this page, and this is where the definitions are. And so if you have those around, you can look at them. But what I want to do now is stop this one and go to another one where we will see, hopefully, something to make some understanding take place here. So suppose that I have a set and a point. Now, in the top picture that you see there, I haven't identified where the point is. We're just talking about a set and a point, okay? Now, what we do with the set, and I'm using 2 dimensions here because it helps. Most people like it better than 1 dimension in terms of sort of understanding what we're talking about. We could be in 50 dimensions. We don't have to have dimensions at all. We're just talking about a collection of objects. Could be you students, and it could be a building as the X naught. There's all kinds of things could be. In any event, what we normally do is we place the point somewhere. Now, if I still have the same set D, and I have the point here, this is where the point happens to be. So if I have a situation where this is the way it is, then the point is called interior to the set. And the reason is, yesterday we said it's interior if there is a symmetric neighborhood N that is inside the set. And so the picture would be that there's a circle you put around the point X naught, and that particular circle lies inside the other blob or circle or whatever you want to call the way I described D. So what it says is some neighborhood is a subset of D. So I have an interior point if I can surround my stuff with stuff that's all inside the set. So as we said yesterday, in your room where you are there, you're interior to the room because you're not standing in the doorway. All right. Every part of you can be surrounded by space that is inside the room, and that's an interior point. So this is what the picture looks like for interior point. If I go down a little bit, what's a picture look like for exterior point? Now this would be a different X, but suppose the X happens to have this relationship to the set D. Then it's called exterior. Why is it called exterior? I can find some neighborhood again, not every neighborhood, but I can find one that is small enough that it avoids everything in D. So this neighborhood is a subset of the complement of D. The complement of this particular D would be everything outside. And I use the word outside in an intuitive sense. From a mathematical sense, we talk about exterior. We also use exterior in English sense, but right now this is the mathematical definition. What's a boundary point? Well, if my point happens to be right there, then one thing you would say is every neighborhood, not some neighborhood, but every neighborhood that I draw around the point has something in the set, that's the stuff over here, and something outside the set, that would be the stuff out there. Okay? That makes a boundary point. Okay? So, now, we also have something called isolated point. So if my set D happened to be, now, this indicates all the numbers between 1 and 2, including, when you write brackets like this, it means you include 1 and 2. It's called the closed interval. But if my set D were all those points and 3, or to put it more mathematically, if it's all those points or 3, then this point is called an isolated point. And the reason is there is some neighborhood around 3 that doesn't have anything else from the set in it besides 3. So this is isolated. And to make a small joke here, some of you understand isolation because of your personality. And that's meant to be humorous. Okay. Since the pandemic spread, we all has been going, we all understand the concept of isolation. All right. We're supposed to socially distance. What that does is it isolates us. Okay. So now, to try to describe this set, it's the set of X such that. The straight line always means such that. X is between 1 and 2, and greater than or equal, less than or equal, that has to do with including, or X equals 3. That's how I would describe it. Now, I'm going to turn the page over and try to explain some things. Okay. In the text that I had on the screen, those words in that handout, we have 6 examples. The first example is when the set D is the interval 0, 1. Now, I left my circle sort of stuff. I'm now just in one dimension. Okay, so I'm on the line somewhere. So if I know where 0 is and I put 1, then I'm on the line 0, 1. This is the closed interval 0, 1. That's what we call it. Okay, what are the interior points to this picture, to this interval? The answer is the open interval. Now, I use square brackets. Sometimes we use parentheses, but I use square brackets to say the point 0 and 1 are not in the set. So this indicates everything between but not including. It's called the open interval. What's exterior to the closed interval? It'd be everything over here and over here, and we write that as everything from minus infinity to 0, not including 0, everything from 1 to infinity, and we want to talk about both, so we say union. It's everything in one place or the other, not intersection, union. The intersection would be empty. The union means everything over here or over here. What's the boundary? The boundary of this set consists of 2 numbers, 0 and 1. Those are the only numbers that every neighborhood of either one of those numbers contains something inside and something outside the set D. What are the accumulation points? Now, I'm starting to also use some symbols. We're going to use accumulation point by putting a little prime on here for the set. So D prime means the accumulation point. The accumulation points of this particular set is D, everything in D. So everything in a closed interval is an accumulation point. What are the isolated points? There aren't any. The empty set. Okay, that's first example. And we say D is a closed set. An open set means every point's interior. Okay, something else we're going to find out is if a set is open, then its complement is closed. And if a set is closed, its complement is open. Now, Everything from minus infinity to 0 is an open set. Everything from 1 to infinity is an open set. The complement is the closed interval, so it's a closed set. There's several ways we're going to be heading and talking about this. That's just one. All right, this was example 1. What's example 2? The interval from 0 to 1 without either 0 or 1. This is called the open interval. Okay? What are the interior points? And the answer? D this time. Now, in the previous example, we had to throw away the 1 and 0 to make the interior, but now this is the interior. So it is an open set. Okay? What's the exterior? Same as before. Now, this next thing, I put in another symbol. This is what we call sometimes the boundary of D. This little delta sign is called a del, D-E-L. It's, when you write that, you're asking what is the boundary. The boundary of this particular set is, again, the numbers 0 and 1. It's just two numbers. That's the boundary. Okay? Now, what are the accumulation points? Remember from before, that's what we mean. Every point is, again, an accumulation point, except maybe you will agree that this is wrong. What about 0 and 1?
It shouldn't be included because it's a closed set.
0 and 1 are accumulation points. Is that right? Accumulation point means every neighborhood contains a point besides 0 or 1. I mean, every neighborhood of 1 contains a point besides 1 in the set. And if you think about it, that's true. Therefore, what I wrote is wrong. Okay? Now, I know that, but I was hoping when you looked at it, you might think, oh, there's something wrong with that. So what do I need to do for accumulation points here? I need to include 0 and 1. Okay? Sometimes I'll do that. Sometimes I'll just make a mistake, but sometimes I do that on purpose. Okay. Make more mistakes than doing it on purpose, unfortunately. The isolated points, there aren't any. Okay, third example.
Can I ask a question about the second example, Professor?
Sure, please.
Okay, I'm confused because why aren't 1 and 0 also exterior points?
Because exterior means you can surround, let's say the point 1, because we have to separate the two numbers. Take the point 1. We can surround 1 by something called a neighborhood that only contains the points. Now, either outside D or inside D, depending on what we're talking about. We're talking about exterior, you can surround. So if you're outside the room, we could surround you with space that is also outside the room. I don't want to put you in a ball, okay? Mathematically, we could put you in a sphere that would be outside the room. Now, for that, you'd have to kind of crunch up and, I mean, so I just basically say space around you. So the point is that any ball around 1 will include points less than 1. And that's stuff in the set. So any ball, in this case, any interval around 1 will have to include stuff less than 1. And therefore, that's inside. So 1 is not an exterior point because in a non-mathematical way to say it, there's no distance between the set and 1. Okay? You can get as close to 1 as you want and stay in the set. And therefore, it can't be exterior. Exterior means it's isolated from the set. Does that help?
Yeah, thank you. I think I understand it now. Thank you.
Okay. Everybody ask when you need to, please, and ask again if you don't get it. The next example is the numbers from 0 to 1, but this time I left 0 out and I included 1. This is called half open or half closed. And I also threw in 2 by itself. Okay. So I kind of overemphasized this because I wanted to show you I changed it. Before, this has been inside when we had this. Now I'm not including 0, but I am including 1. So I kind of made it heavier. Looks like a bad mistake, but anyway, it's an attempt to make it heavier. Okay, what's the interior? Now, I threw another thing at you. Interior, we put a little 0 up here. That's the way mathematicians talk about interior of a set. Put a little 0 there. So this is red, the interior of D. That would be everything from 0 to 1, not including 0 or 1. That's the interior. If you take any point, like a half, you can surround it by something that stays inside 0, 1.
Wait, wouldn't 1 be included too, since 2 is part of it, I guess?
2 is part of it, but the space in between is not.
Okay, so yeah, okay, I get it.
In order for you to be interior, you have to have an interval around you, which is in the set.
Okay.
Okay. And
So
by
one
the way,
point
you got to take time to think this stuff out. Okay. It's not, and this is not a put down. It's not really very hard once you see what we're talking about, because it's very precise, exactly what it says. On the other hand, you're not used to precision like this. Okay. So it'll take a little while to get it. Once you get it, it'll be like, oh, this is easy. Okay. Now, but I think these examples will be helpful. What's the exterior? Yeah, it's everything up to 0, but not including 0. And it's everything between 1 and 2, but not including 1 or 2. And everything after. Now, I just said in my English description a bunch of ands, but that's the English. What we really mean is or. It's a point in one set or the other set or the other set. And so mathematically, we put unions here. Union is where you have or. This is where we collect everything, throw everything together. Okay. What's the boundary? What are the boundary points? Well, 0 and 1 and 2 is a boundary point. Why is 2 a boundary point? It's a new kind of boundary point, but it's a boundary point because every neighborhood of 2 contains a point from the set, namely 2. And a point not in the set, namely 1.9 or something, or whatever. So the boundary is 3 points this time. So isolated points are boundary points. What's the accumulation points? What points in this set can you get close to? And the answer is everything from 0 to 1. You cannot get close to 2. You can't be in the set and be close to 2 because there's a neighborhood around 2 that doesn't have anything to set in it. Okay. The isolated point is just 2, and that's that. Okay, there's 6 examples. That's 3 of them, and I have 3 more, and they get harder. All right, so you can't see anything now. So we have the empty set as an example. All right, suppose I have any finite set. Take 100 numbers. Take 5 numbers. Take 1 number. Any finite number of numbers. Okay. What are the interior points of that set of numbers? If I have the numbers 1, 2, 3, 4, what intervals are inside that set? And the answer, there aren't any intervals inside that set. There's no neighborhoods inside that set. So the interior is the empty set. If I have a bunch of discrete points, there is no interior. There's no region around a point in the set that stays in the set. So the empty set is the interior. The exterior is everything out that is not in the finite sets, everything else. The boundary is the set itself. In a finite set, every point is a boundary point. The accumulation points, there aren't any. If I have a finite set, I cannot get close to any of them. They're all isolated. Okay?
So what this would look like on a graph would just be a bunch of points on it all by themselves, right?
Yeah. Tell me again, what's the set?
What?
What is the set you're talking about?
Oh, example D. If it's a finite, so it's a finite set. The
You
points
have a finite set. Yeah, go ahead.
the points are just all by themselves on a graph. So like one could be at 1, and then another one could be at 2, but they're not connected. So it's just they're just by themselves.
Yeah, but you use two words there, non-mathematically, and that's okay because you're trying to describe. You use the word connected, okay, and you use something else I now lost. Forgive the phone ringing. I thought I had deadened that. It'll ring about 5 times, and then we can. Okay. That happens to be the Republican National Committee calling. I get calls from the Republicans and the Democrats. It happens to be Republicans calling from New York City. I ignore them. I also ignore the Democrats and the communists and the atheists and everybody else that call me, and the Christians and the Jews and anybody. I ignore everybody when I don't know them. So this is all on the line. I'll have to probably edit this part out of the video, but anyway, it's meant to be lighthearted here. Sorry about the phone ringing. Okay, so the isolated points, what, as I said, you said some other word there that I'm trying to remember what you said. Because what you're trying to explain stuff, you're saying stuff's apart, stuff's away, is, you know, and that's why mathematically we use these words interior, exterior, boundary, accumulation and stuff to say mathematically what you were trying to describe.
Mm-hmm.
Okay?
Yeah. Okay, I think I get it.
Okay. We're going to talk about connected sets later. A set's connected in the real numbers if, take any 2 points in the set, the interval between the points is in the set. That's what a connected set is in the real numbers. But we don't need to know that yet. Okay. Next example. 2 more examples, then we'll do something else. Example 5 is the numbers 1 over n, where n is a non-zero integer. So 1/2, -1/12, plus 1/100th. These are all the numbers in the set. Okay. Now, this is not a finite set. This is called an infinite set. And one of these days we'll be talking about the difference between finite and infinite, but not yet. Anyway, you know what these numbers are: 1, 1/2, 1/3, 1/4, 1/5, and so on, and -5, 1/5, bunch of numbers. How does this differ? Well, if you think about the numbers, they kind of bunch up. They kind of get close to 0. As n gets big, the numbers get close to 0. And we haven't defined close yet, but that's where neighborhoods come in. Anyway, what's an interior point of the set? And once again, this set does not have any interior points. There's no intervals of members of the set inside the set. So the interior is the empty set. The exterior is everything that's not named here except 0. Okay? 0 is also in the complement, but it's not exterior. So any non-zero number that's not one of these fractions except 0 is the exterior. Why is 0 not an exterior point? Because every neighborhood of 0 contains one of these points. You give me any distance around 0, I can get an n big enough so that 1 over n is inside that distance. If you say I want to talk about everything between 0 and 1/2, then I'll say 1/4 is in there. If you say everything between 0 and 1/1,000,000th, I'll say 1 billion, 1 over 1 billion is in there. So you put any interval around 0, it contains points from the set D, therefore it cannot be exterior. All right, anyway, the boundary. The boundary is all the numbers of D and includes 0, which means union, put in 0. So the boundary is everything in the set with also 0. What are the accumulation points of this set? There's only one accumulation point, and that's the number 0. There's only one place where all these numbers get close to, and that's the number 0. So this is a harder thing to think about, but maybe it helps you. And then finally, we got the hardest one to think about, and that is, suppose D is the rational numbers, all the fractions in the number system. What are the interior points? And the answer is the empty set. What does that mean? There is no interval of real numbers that is exclusively fractions. In other words, between any two fractions, there is a non-fraction. Between any two rational numbers, there's an irrational number. And between any two irrational numbers, there's a rational number. So there is no interval of real numbers that is all fractions, and there's no interval that's all irrational numbers. Therefore, you have rationals, irrationals interleaved everywhere in the real number system. So the set of accumulation, sorry, I should be doing interior. So that's not, this is actually a mistake that's not meant to be there. The interior is the empty set. It should be the 0 here. That's not an intended mistake, that's just a mistake. All right, the exterior is also the empty set. The boundary of this set is all real numbers. Every real number is a boundary point of the rational numbers. What does that mean? You take any real number you like, take the square root of 2. Put in any interval you like around it. It will include rational and irrational numbers, and therefore it is a boundary point. What's the interior? I'm sorry, what are the accumulation points? Everything. Every real number is an accumulation point of the rational numbers. So this one is strange. And there are no isolated points. Now, these are going through the 6 things that are in the notes there, examples 1 through 6. This is just trying to spell them out rather than just write them out. And I want to talk about something else now, and I'm going to go back to the other notes, but since I'm on this, I may as well go ahead and say this. One of the things we describe here in the class is the Cartesian product of 2 sets. Now, it's easy in terms of what we mean. We write AXB, this is read the Cartesian product after the person named Descartes. Cartesian comes from the name Descartes. The Cartesian product of A with B is the set of all pairs that you get, ordered pairs, where you take one element from the first set and one element from the second set and pair them up. All possible ways to do this is what the Cartesian product is. Now, by the way, when you define what you mean by whole numbers, by counting numbers. In other words, when you start with sets and you create the number system for the first time, okay? This is not whatever happened historically or whatever, but if we try to explain what are the counting numbers, then the Cartesian product is how we define multiplication of numbers. What we do is we take a set with 2 things in it, we take a set with 3 things in it. We say the multiplication is the cardinality of the Cartesian product. In other words, cardinality means how many. If I want to know what 2 times 3 is, I take a set with 2 elements. I take a set with 3 elements. I find the Cartesian product, which is a bunch of pairs, and I count it. When you count the Cartesian, the pairs here, you will get 6. So we define multiplication after we've defined what numbers are by talking about the multiplication of 2 numbers involves the cardinality of the Cartesian product of sets representing that amount of numbers. Now that's not part of our course. I just thought that might be something of interest to you. But we use Cartesian products to define multiplication of numbers. We use union to define addition. But we use Cartesian product to define multiplication. Anyway, pictorially, if you want to make a plane and you want to put the 1, 2 on the x-axis and the 2, 3, 4 on the y-axis, then the pairs become points in the plane. How many points do we get from this Cartesian product? And the answer is 6 points. Okay, that doesn't include the numbers here on the axis. These are just indicating tick marks. It's the 6 things up here. If I take the whole real numbers Cartesian product with all the real numbers, what do I get? Well, notationally, I get R2. We call that the plane. And what is it? It's a set of all ordered pairs where the first number is a real number, which we pick from the x-axis. The second number is a real number, which we pick from the y-axis. So you can think of the plane as a set of ordered pairs, and it's a Cartesian product of all the real numbers with all the real numbers, which we write this way in order to make a graph. So slowly we're beginning to get to section 1, because now we have a coordinate system. One of these days you'll look back and say, how do we go so fast? We were going so slow at the beginning, I got sleepy. All of a sudden he's in chapter 5. And that may happen next week, watch out. We're reviewing now. We're reviewing is slow, but I think you're learning a lot of new stuff too. Okay, I want to go back to some other notes here, so I'm going to stop this share. You're going to see my ugly face for a minute, and I'm going to go to another share. Okay, now I'm going to first go to the share we had already. In case you hadn't noticed, these examples right here on the screen, those are the examples I just wrote out for you on the paper. Okay, what's before this stuff? There's some notation and the Cartesian product and intervals. And so this is a page of notation. I've been using that notation in the pictures I drew here. This is a closed interval and so on. If I bring in infinity, you never include infinity. You always have an open thing for infinity. And so you can look at this page to get the notation that I've just been using for sets. And so I thought I'd mention that. So now I want to go to the next set of notes. So I'm going to see me again, and then I'm going to go to another screen here and go to this screen. So we should be having now a new set of notes to look at. So in this set of notes, I start out by rewriting what a Cartesian product is. And I do a little bit extra stuff, namely, if we have the empty set as one of the things, so I can't make any pairs, then the Cartesian product is the empty set, okay? R2 is called using plane. Every ordered pair is called a point in the plane. And so all I'm talking about on this first page of these new notes is what we do to make up a graphing system. We have a vertical line and a horizontal line, x-axis, y-axis, all this stuff you know, okay? So I'm trying to delineate it in case you never saw it before. Okay. Now, in terms of never seeing it before, what's on the screen now might be brand new to you. What is a relation? It's my Aunt June. No, that's not what I mean. A relation is a set of ordered pairs. If R is a relation, then the inverse of the relation just turns the pairs around. Simple. So if you know what the pairs are, you turn them all around, you get what's called the inverse of relation. So I write down here, X and Y is in the inverse of the relation. That's how we denote it. If and only if YX, see, I changed the order, is in the original relation. Okay? Now, a relation is a subset of a Cartesian product. Why? Cartesian product's a bunch of ordered pairs. What's a relation? A bunch of ordered pairs. Okay? So if I take some things, for example, out of the real numbers, like I took those 6 numbers a while ago, 1, 2, and 1, 3, and so on, those 6 numbers, that's a subset of all R cross R, all R2. And so a relation is a subset of a set of ordered pairs, a subset of a Cartesian product. Now, so if I have a relation, now, suppose we take the relation, and a lot of things in life involve relations. Once we define this carefully, we can do a lot of math involving things in life. For example, suppose we take the relationship to have more money than. If you think about saying more money than, having more money than, you're talking about so-and-so has more money than so-and-so. So what we're doing is pairing up people. Okay? So we could take the set of people as our universe, and we could take a person and compare them to another person by this relationship, namely, person A has more money than person B. Now, it doesn't mean it's true, because it might be false, but we could compare them. Okay? Now, if it's true that person A has more money than person B, then we put that pair of people in the group, in the relation. In other words, those two people are related. So we pair them up and we put them in the relationship. Okay? So you could have, for example, if we all got together with your families and stuff, we could pair up people by who is the spouse of whom. And we can say so-and-so is the spouse of somebody else, or the partner. I mean, I don't care what we say about the relationship, but the point is we're pairing up people when we do that. And somebody can say, oh, is that your wife? You say, no, that's not my wife. So that person and I would not be paired with the relationship is the spouse of. Okay? Anyway, when we have a relationship, a bunch of ordered pairs, the second thing in the pairs, all the points, all the things that are second is called, well, sorry, let me say it. I'm looking at my watch and seeing 18 after here. The domain is all the first things. So it's all the X's for which there's something Y in the relationship. Now, if I'm talking about the spouse of, and I'm in Utah, I might be paired with more than one person. Okay? Because in Utah, maybe it's legal to have more than one spouse. And if it's not, then maybe we can go to some other country in the world where it's legal. Anyway, the point is it's possible to have pairs with the same first person or pairs with the same second person and be different pairs. So all the pairs, all the first things that are in the relationship is called the domain. Utah, I bet it would be more like something. Anyway, I don't know what that's about from Mac. I'll read that later. Okay. The range is all the possible second things that are paired up. Okay. Now, any set containing the domain is called the source. Any set containing the range is called the target. And we don't have much time here, but what's in these notes is talking about relationships. Now, what we're working on, and by the way, one of the hardest things that we're going to be dealing with is the composition of things. And so this is describing the composition. I don't have time to talk about it because it's 19 after today, but you might want to look at that definition. Tomorrow we'll talk about it. And we talk about image and inverse image and many-to-one relation and single value relation, because what are we trying to do? We're trying to get to section 1 of the book, which is describing a function. Mathematically, to describe functions, we need to understand ordered pairs. And so what is said here is a function is a many-to-one relation. Okay, that's what a function is. And we're going to be talking about this tomorrow. So tomorrow, we're officially going to be in section 1 book-wise, except you won't see anything like this in section 1. We're going to be in these notes talking about what a function is. And later down here, you'll see more things like you're used to when somebody talks about functions. The thing is to say that x squared as a function is wrong, but we'll talk about it. And then we have onto functions and one-to-one functions and things. And once we get that done, about the end of page 4, we're going to stop looking at the notes and not worry about the rest of it. All right. So tomorrow, I'm going to talk about these, like pages 1 through 4, maybe 2 through 4 in these notes. And then we're going to go into the book and start doing the book. And you guys have already done exercises. So I'm just going to talk about what's in sections 1, 2, and 3. And we actually may start calculus tomorrow, which is to talk about functions and pretty much in the way that you have been used to. Okay. All the stuff I've been talking about so far has been to give you background and stuff we can rely on later. And then hopefully you have been reviewing a lot of algebra and trigonometry so that once we start using it, you are caught up on it. Okay. Well, I'm going to stop the share and somewhere stop the recording.